Our first flash talk is by Miguel Ohnesorge and Asia Watkins.
Okay, thank you. Yeah, we're going to talk about the philosophy of the geosciences, what it is, what it can be, what it should be. And one way to frame what we're doing here is to motivate that people like Asia and I, me working on the history and philosophy of physics, Asia working on biology and climate science, should actually understand ourselves as being engaged in a common philosophical field, and motivate others perhaps to understand themselves as well as being engaged in that field, which is the philosophy of the geosciences. Now, what we want to motivate is why there should be a philosophy of the geosciences and why there already is a philosophy of the geosciences, which raises a much broader meta-philosophical question. It's sort of an instance of that. Why do we do philosophy of any particular sciences? And that some intuitive responses to that, I think, that anyone can think of, which is many different forms of inquiry share methods, so we might want to study them together, or they share a theoretical framework. And one might think, if one looks at the history of disciplinary integration of what we now call the geosciences or earth and planetary sciences, that is also roughly the case. They have all sorts of different backgrounds, from practical mining and surveying, navigation, to astronomy and meteorology. They gradually converge with some physical questions like the tides or the shape of the Earth being studied in celestial mechanics, and some questions about geology and fossils and collecting being studied in natural history. And these two branches of studies become further independent around the beginning of the 20th century in geology and geophysics as well. And then we have the earth sciences. Now we study other planets, so we do earth and planetary science. Seems like there's some sort of convergence happening, but that is actually not really true. If we look at the history more closely, this is still a toy version of the history, very much apologies to any historians. For example, there's lots of blues here, theoretical innovations, and oranges, methodological. In fact, the geosciences become much more theoretical and methodologically diverse over history as they become subsumed in one field. Geology has its own historical revolution. Rachel Auden has written about this very nicely. Of course, paleontology uses Darwinian evolutionary theory. There's a whole new branch of empirical study and theory coming from elasticity theory. It starts with teleseismic observations in modern seismology that finally gives us access to the internal structure of the Earth. There's the theory of plate tectonics. Famously, that becomes accepted in the middle of the 20th century. Get a new theory. Now we use things like artificial satellites. We have exoplanet observations, which look much more like astronomy and astrophysics, and so on and so forth. So things, both methods and theories, become more diverse. So this disciplinary integration does not reflect any sort of methodological or theoretical unity of the geosciences.
Okay, so instead of thinking about philosophy of the geosciences as unified by a common method or theoretical framework, what we instead want to propose is that the geoscientists, despite heterogeneity among them, share a common set of problems arising from what planets are like to study. So a lot of the excellent debates in philosophy of the geosciences, so in philosophy of climate science, philosophy of paleontology, philosophy of the geophysics, have sort of like seemed to happen separate from one another. And our contention is that, in fact, the questions in each of those sort of subfields share some foundational topics of interest. Okay, and we think it's going to be more natural not to see these kind of disparate fields in philosophy of the special sciences as truly disparate, but actually as connected by some underlying challenges faced by the scientists. Okay, so now I'm going to tell you what those things are. So our proposal is that there are some shared epistemic problems faced by geoscientists arising from the nature of planets. So the layered structure of planets, their relative size, the complexity of them, the fact that a lot of the phenomena we're trying to study are in the deep past. So these challenges are the following. First, planets and planetary processes are often really hard to access directly, which leads to scientists relying on a lot of like surrogative reasoning, like models, simulations, analogs, in order to study what they're really interested in. Second, the subject matters in philosophy of the geosciences, and then subsequently philosophy thereof, are hard to manipulate. So we can't take these phenomena into a laboratory setting and study them there like we can in some other sciences. Third, the subject matters in the geosciences are often really hard to generalize from. So there's like particular episodes in history or particular planets or particular parts of planets, and scientists will study those, and then they won't, it's not straightforward to say how they then generalize those results to other planets or other periods of time. And then finally, in the geosciences, we think in particular, although of course in other sciences this is difficult as well, it's hard to establish cause and effect relationships. So one of the things, for example, that happens in the historical sciences is that a lot of times we have data that says like one thing happened at roughly the same time as another thing. But in order to establish a causal relationship between those two events, you would have to show that one occurred prior to the other. And lots of times in the geosciences, we just don't have the kind of data that allow us to make those claims. Okay, so for the rest of the talk, we're basically going to argue that it's useful to think of philosophy of the geosciences by reference to these four shared issues in the geosciences, and we're going to make that argument by just looking at some cases. So I'm going to talk about two kind of chunks of the literature in philosophy of the geoscience that now are like pretty well known. Some of you may have read some of this, and I'm going to suggest that those existing debates also make reference to these kind of four foundational issues. And then Miguel is going to talk about some of his work that we think can also be kind of like diagnosed, like what's interesting about it also makes reference to these four foundational issues in the geosciences. Okay, so here's the first example. Again, like for the sake of time, we won't go into all the complexity of the literature here. But there's been a debate in philosophy of the historical sciences, so historical sciences like paleontology, historical geology, archaeology, about whether they're different in a substantive way from the experimental sciences, and if they're different, whether that difference makes any difference for how epistemically optimistic or pessimistic we should be about the likelihood that those sciences are going to produce claims of knowledge. So there's sort of three positions on this question in the literature. One is that there is a difference between the historical and experimental sciences, and as a result of that difference, the historical sciences are in a worse position epistemically. The second position is that there is a difference, but it's a difference that doesn't make it the case that either the historical or the experimental sciences are in a better or worse position epistemically, so it's kind of a wash. And then a third position is actually the purported differences between the historical and experimental sciences have been overstated. So both historical scientists and experimental scientists rely on a wide range of methods, and we can't like characterize those methods homogenously. Okay, so what we think is like some of the interesting stuff underlying the debates about these three positions also has to do with these four common challenges that we've already referenced. So we actually think all four of these come up in this case. So this debate is about planetary processes in the past being hard to access, hard to manipulate, hard to generalize or reproduce, and some claims about cause and effect being hard to establish. But I'll just say a little bit more about the manipulability one. So one of the supposed differences between the historical sciences and the experimental sciences in particular is that the historical scientists can't manipulate their subject matter. And so that claim of difference really drove these three positions. Like they focused on manipulability or lack thereof in the historical sciences as the reason for making their arguments. Okay, second example, so again, like ostensibly totally different area of philosophy of science. This example has to do with climate model evaluation. So here there's a problem, which is we use climate simulations as one of the main sources of evidence to learn about contemporary climate change. But climate simulations are actually really different from the climate itself. And so the question is like, why would we think they're a good source of evidence given some of those differences? And one of the more influential answers that's been proposed to this is due to Wendy Parker's work. So she says instead of evaluating models by their similarity to their target systems, we should instead evaluate them just by their adequacy for a purpose. Okay, again, this is like, there's a lot of literature here that I'm not going over, but I hope I've said enough to just illustrate that, again, part of what's kind of underlying the interest, the philosophical interest in this debate, we can make reference to these common challenges that geoscientists face here. So again, we think in this case, all four of the challenges actually come up, but for the sake of time, I'll just say a little bit about the first one here. So the climate itself is actually really hard to study directly. So we are directly exposed to some of the effects of climate, like weather and ecological changes and things like this, but the climate as a whole phenomenon is really difficult to study itself. And as a consequence of that, climate scientists rely on simulations as one of the main sources of evidence. And so it's the fact that we have this difficulty of access that drives the scientific practice, reliance on simulations, and thereby drives the philosophical interest in how those simulations are used as a source of evidence. Okay, let me just super briefly recap what I've said before I hand it back to Miguel. So the claim so far is just that the debates about the difference between the historical and experimental sciences, and also debates about how to evaluate climate models, have this kind of common foundation in issues that come up in many of the geosciences. Those are just, I won't go through them again, but the same 4 things that are on the right here. And what Miguel will talk about is like maybe we can use these same 4 foundational challenges in the geosciences to diagnose the potential for future work in philosophy of the geosciences.
Okay, and I'll go through 2 examples. They're not just my work, but I have worked on them too. I'm working on them. The first I'll go through is the example of quantification in seismology, which exemplifies problems in quantifying in geophysics more broadly. I'm working on this with my colleague Christian Laroli Filippi, but this work we're drawing on by Teru Miyake that's been very foundational here. And the big problem is that we're interested in is how seismologists came to establish a scale, a quantitative scale, represent earthquake size as a scalar magnitude, when it's impossible to experimentally manipulate or shield earthquake sources from the many disturbing factors that affect the propagation of seismic waves and that happen during the dynamic of the source, the wave generating process at the source. And this is interesting because the standard view coming out of measurement theory and coming out of debates on how the measurement theory is applied empirically takes quantification regularly to require some sort of experimental evidence, meaning that what we do if we want to test whether we have a quantitative scale here, whether we can take a relationship between a measurand and some indications and build a scale, is that we first have to shield the causal relation that we take to purportedly apply to the measurand and the indications, and then we trigger variations in the magnitude of the measurand and observe whether there's some constant corresponding variations in the indications, and then we can construct a representation theorem. Prove that we have a quantity there. It's impossible in seismology. We can't experimentally manipulate the magnitude of earthquakes or earthquake sources, and we can't shield the transmission of seismic waves from the internal structure of the Earth, particularly because we want to understand that structure. So how did seismologists manage to quantify earthquake size? Is that it looks quite different from these standard models of quantification. They did succeed, on our account anyway. And they did it by constructing a purely phenomenological place order scale. That's a scale everyone will know, the Richter scale. It just defines magnitude in terms of the common cause of amplitudes recorded at different distances, which is approximately convergent locally back then in Southern California when lots of other things don't vary. And the types of seismic waves we're picking up, the kinds of media they're traveling through. Then we extend it as expected. Once these factors vary, there's lots of empirical discordances. So we end up with many different magnitude scales corresponding to different types of waves and different kinds of media. And then eventually we develop a refined scale. It's actually physical. The moment scale has physical dimensions that's based on a physical model that accounts for these discordances. The evidence here is not shielded manipulation of a quantity and tracking its effects, but rather is that by presupposing quantitative relation, we discover many new, robustly verifiable details about the Earth. Again, why is this interesting? Because it asks how do we quantify under conditions that are different, that are unique to the geosciences in some respects and are different from the cases usually studied in the literature. I know we're running late, but I'll go through one other example I've been working on with Alisa Bokolic and Matilda Carrera, the forthcoming paper. That is the problem of understanding the causes of the tides, specifically the solid body tides, which are the tidal deformations of the continents, not the oceans. They're also moving quite a lot, actually. And that's an interesting problem because we've had a good gravitational tidal theory since Laplace's work in 1780, but we struggle to actually predict the magnitude of displacement it would cause on the continents until the late 20th century. Why is that so? Because there's so many physical properties of the Earth that make a difference in particular places and globally. I have a list here. I won't run you through them. We can talk about it in the Q&A. And the problems that geodynamicists faced for many years was how can we then attribute, given all these possible things that could make a difference, the difference they make in particular cases to specific causes. And the solution that we identify is this method of residues that goes back to John Herschel's work. Teru Miyake has worked on that as well, which is sort of a method of causal approximation where we first model the dominant causes, then we expect the model to give us wrong predictions in particular cases, we record the residues, and we attribute the residues to further causes that we study based on their signatures. We include those new models in our initial model, and so on and so on and so on. This succeeded in geodynamics. Again, why is this an interesting case? It's an interesting case, I mean, in this case particularly because of the challenge of causal inference, but we're facing a problem where theory doesn't give us the results we would expect it to give predictively because of the causal complexity challenge that we face when studying a real complex and large system like the Earth. Okay, to wrap up, and I think we're almost in time. Yes. We just try to motivate really that we should study the philosophy of the geosciences as we treat it as its own little subfield in philosophy of science. Why? Because the geosciences are structured, even though they're methodologically and theoretically heterogeneous, around a set of shared epistemic problems arising from the nature of planetary processes and planetary properties. And we show that this implicitly already drove some interest in classical debates on the geosciences, such as the distinction between the historical and the experimental science, and the debate about climate model evaluation. And in fact, it can also lead us to further areas of work, such as looking at, in the case of epistemology of measurement or measurement theory, as quantification and seismology, or looking at causal inference in geodynamics. Now, we want to note briefly, in fact, this is all going back to a paper that we wrote that you can read, that we think this idea of understanding the philosophy of the geosciences as a field structured around shared problems can also be extended to philosophical issues that have not received the attention that they actually deserve, which is the ethics and the politics of the geosciences. The key feature here is that the geosciences do not just share epistemic problems, but they share a common history as sciences almost exclusively funded by colonial trading companies, oil conglomerates, and national state governments. And as a result, in virtually all geosciences, the data that we have is highly asymmetrically distributed, but we're now in a situation where we have to rely on the data in giving advice on global policy issues like climate change, or we have to do earthquake recordings and so on and so forth. And all this data is tainted by their history. So that's the real challenge of how we can use that data now and how we can do that in a just or in a fair way. And again, we think this is a shared problem across these fields, given their shared history, and it pays to study these problems alongside each other. And in the paper, we actually go through some of that work that's just beginning to start on these political issues. And that's it from us. Thanks for listening.
Thank you very much. Very interesting. I'd like to suggest to you the royal road to success for this project. Write a book. The title is The Philosophy of Geoscience. The press should be either Cambridge University, Oxford University, Pittsburgh University, Minnesota University, or Chicago University Press. Why do I say that? Here's the inductive base for the prediction of success. Look at the careers now in decreasing importance of Thomas Kuhn, Paul Feyerabend, Heather Douglas, Marcel Weber, philosophy of experimental biology, and in the end, mine. Thank you very much.
Okay, I think first of all, we're very flattered to get this suggestion. I want to say, because Miguel won't say, that he has a book contract with the University of Oxford University Press, with some of his work on geophysics. I think probably one book project per junior scholar is like maybe enough. I also should say, it's kind of like in the works for us to do like an edited volume on this. I think that's kind of at least like more in line with how I see this field. Like, sorry?
It's got to be a bang in the beginning.
Okay. I mean, we're happy with the bang. Yeah. So we'll take it.
Yeah. And Alisa Bukulic is also writing a book on some of these issues. Yeah.
Thank you for your talk. I have a question about causal inference, because in what you're describing, there seem to be pretty strong parallels to debates in and around the social sciences and causal inference in the social sciences. And in that domain, there seem to have been kind of two major responses to the issues around, impossibility of experimentation and manipulation. And one is to develop methods for causal inference with observational data. So that's what the whole credibility revolution in the social sciences is about. And the other response is to kind of make causal inference less central of an epistemic aim than it has been. So I take Marcus Aronen to have been making that argument, focusing not so much on establishing causal relationships, but he argues perhaps we should be looking at something like robust patterns or something like that. So I wonder, in the geosciences, do you see like both of these responses, or is it maybe more kind of leaning one way or another?
Well, it's a good question. I'm not sure if you want to say something on climate science, but what I'll say is that the case is unique insofar in that you're looking at a geoscience, the one I talked about, geodynamics, that is sort of firmly rooted in like Newtonian mechanics, right? So there's this nice privilege you get, which is that causes are additive because they're forces, and you can express all the relevant causes in a way that you can add them up. And so that's sort of one presupposition for the kind of causal inference method we're describing here. It's like, so it makes sense. I think in geophysics, no one would doubt, they don't use the language of causes a lot, but no one would doubt that what we do is we build approximations and then we refine them and we add further like terms and that have physical significance and we get a better result. That's, I think, most of the work that's happening. But I think it would be interesting to look at like the messy bits with the physics and perhaps the biology overlap. You could think about stuff like mineralogy, or chemistry, in this case, mineralogy, perhaps soil science. I don't know, you know more about this. Where you have like some different problems because you are not just talking about forces and stress and strain and so on. So there's like a lot of interesting work on ordinal statistics, for example, in causal inference, where you don't have quantitative scales and you have to talk about ordinal attributes. In soil science, I know. But I can't give you a very good answer because I've mostly looked at the physical part of the geosciences where the additivity is not really a question. So some of the more thorny problems, I think, that plague the social sciences, because you have like sort of different kinds of causal complexity, right? Additive causal complexity, such as in geodynamics, and then you have causal complexity as additive, and there has a heterogeneity problem. Yeah.
So there's a couple more questions in the queue, but we only have time for one.
Thank you. I thought that was really interesting. I was wondering, do you guys think that there really is such a, heterogeneity in the methods? Or do you think it's maybe more of a perceived heterogeneity because of the degree of surrogative reasoning used?
Do you want to do it?
Sure, yeah. It's an interesting question. I'd be happy to talk to you more about this at one of the breaks. One of the really important developments in philosophy of the historical sciences was to point out that the historical sciences aren't just based on trace-based reasoning. So traces of the past are not the only kind of evidence that historical scientists have. They also have like all this surrogative stuff. And for me, at least, like that's enough to establish the heterogeneity claim. Like we got traces and we got models. Like there's more than one, but maybe there's like something deeper in your question. And so that's why the promissory note to talk later. Yeah.
I think there's a big question about how, what's the grain at which you ask for heterogeneity, right? Like you can look at instrumentation, and things will obviously be heterogeneous, but then there's some higher level. In a way, our claim is like there's first order heterogeneity, but then there are some commonalities, but they're less in the methods, but more in the way that the methods are applied and how you have to justify them in particular contexts. Just to say I'm agnostic, but.
Let's thank Miguel again.